Thank you to the organizers for giving me the opportunity to present here today. So the title of my talk is a little bit broad, but what I really want to focus on today is the last part, which is the dissipationless transfer of spin via charge. Now, the reason why I put these three elements, the writing, the reading, and the transfer of spin via charge together, is partially because I've dedicated quite a few years of my research to the first two. But most importantly, it's because there is a linking element, a very important element that links all three of them together. And this element is the spin-orbit coupling in the presence of a break in inversion symmetry, which gives rise to the spin-orbit field. Now, this work has been put on internet recently. It's the fruit of a collaboration between the University of Cambridge, both the Cavendish laboratory where I'm from and the Department of Materials, and three universities in London, UCL, Imperial College, and Royal Holloway. But I want to especially acknowledge the work of Rock Jeon, who is a postdoc and put a lot of effort in this work. Now, this fancy diagram basically wants to attract your attention to the main message of this work, which is we are able to transfer spin in a dissipationless way by transferring it via a superconductor, via Cooper pairs in a superconductor. And as you know, transport of Cooper pairs is dissipationless. But the key element that you see here is also that Cooper pairs are in a triplet state here. So this seems to be in conflict with the standard BCS theories on superconductors, but we'll get to that point. Okay, so just let me briefly run through the first two effects just to introduce the spin-orbit field in inversion asymmetric systems. Now, when you have the break of inversion symmetry in a crystalline potential where carriers move, then you can effectively represent the spin-orbit coupling as a Zeeman interaction by an effective field that is, we can refer to as spin-orbit field, and which depends on the momentum of carriers k. So this means basically that when you apply an electrical current and carriers develop a net direction of motion, a net k value, they also feel the action of this effective magnetic field that polarizes their spin. Now, the way in which the symmetry can be broken is, the symmetry can be broken in many different ways. Now, you're probably very familiar with a bilayer systems in which the surface potential has a uniaxial symmetry break in the out-of-plane direction, which results in the very well-known Rashba symmetry for the spin-orbit field, which basically means that regardless of the direction in which we pass the electrical current in the plane of the interface, the spin-orbit field will always act to polarize carriers in the direction perpendicular to the current direction. However, in the past years, we've dedicated quite a bit of work to another system, which is a ferromagnetic crystal, in which the symmetry is broken within the unit cell of the ferromagnet. And we have recently demonstrated that spin-orbit fields with Dressel-Haus symmetries can be measured up to room temperature in nickel, manganese, and timonite. Now, we have also studied systems in which surface effects and bulk inversion asymmetry effects are coupled together, are mingled together, and which gives rise to symmetries that are the union of Rashba and Dressel-Haus. So the particular system that we studied is iron epitaxially grown on gallium arsenide, but this has also been explained very well by Christian Bach in the first day of this workshop. Now, as far as the magnetic reading via charge is concerned, this is also very much linked to the spin-orbit field. Now, to just intuitively understand it, we can phenomenologically describe the interaction between magnetic and charge parameters in a magnetic system by introducing a Hamiltonian. So the diagonal elements here, for example, this one, connects the magnetic field to the magnetization, and it's obviously the susceptibility. This diagonal element here connects the electric field to current, and is the conductivity. If we had to represent in this matrix the spin-orbit field, so the control of magnetism via charge, this would correspond to this off-diagonal element, which connects the electric field to the magnetization. Now, because of the very fundamental principle of reciprocity, we expect the other off-diagonal element to be non-zero, and this connects, as you can see, magnetic field to charge. The Onsager reciprocity relations also tell us that these two elements are equal, so this means that the spin-orbit coupling affects them in an equal way, and this means that since we can we can modify magnetization via electrical current, the opposite effect is also true. So when we excite spin waves, these spin waves pump electrical current, and by measuring this electrical current, we gain direct information on the excited spin dynamics. We have demonstrated this effect in an inversion asymmetric ferromagnet, gallium manganese arsenide, but this was also shown in when the symmetry is broken at the interface in the group of FERT. So, but now let's get to the core of what I want to tell you about today, which is, so the aim of this experiment was really to investigate whether we can use charge to propagate spin, but do this in a dissipationless way. So you know that charge and spin don't go well together, because so this is why systems like GIG got so much attention. So because in these systems you can disentangle charge transport with spin transport. But this is obviously no longer true if the charge that transfers the spin is made by Cooper pairs in a superconductor, because we know that dissipation is associated to this charge transfer. Now, for this experiment, we considered two different layout structures. In both of them, we had a 6 nanometers permalloy layer sandwiched between two niobium layers of varying thicknesses. And these thicknesses ranged from 7.5 to 60 nanometers. Now, while in the first layout, this tri-layer structure was simply terminated by a copper capping layer, in the second layout, we had a platinum, 5 nanometers platinum layer grown on the opposite side of the niobium with respect to the permalloy. Now, in this graph here, that shows the longitudinal resistance of the structure as a function of temperature. For the different thicknesses of the niobium layer, we immediately identify the superconducting transition temperature of the composite niobium, two layers of niobium. Now, this plot here represents the superconducting transition temperature as a function of niobium thickness. Now, as you can see, when a niobium is grown in contact with the ferromagnetic permalloy, there is an overall shift downwards of the superconducting temperature, and this is because of an inverse proximity effect. So basically, when the superconductor is in contact with a ferromagnet, the exchange field closes the superconducting gap at the interface, so the niobium is less superconducting and the transition temperature is lower. But another important thing that you notice from this graph is that when platinum is grown on the opposite side of niobium, which corresponds to these blue dots here, the transition temperature is not really affected, and this means that any proximity effect is dominated by the niobium permalloy interface, and the presence of platinum on the other side does not have any impact on the superconductive properties of niobium. So the way, so in order to measure spin transfer through niobium, we used a spin pumping layout, where the sample was glued face down on a strip line waveguide, and ferromagnetic resonance was measured in transmission. Now, these are typical ferromagnetic resonances curves, ferromagnetic resonance curves measured for a 30 nanometers thick niobium at different frequencies and different temperatures. Now, this plot here represents the microwave frequency dependence of the line width of these ferromagnetic resonances. It follows a linear trend. From the gradient of this line, we can extrapolate the homogeneous, the dynamic component of damping, which gives an indication on how much spin angular momentum is lost from the permalloy into the niobium. Now, you notice here very slightly in this graph that at low temperatures, below the transition temperature of niobium, the gradient decreases slightly. So this seems to indicate that the Gilbert damping is slightly decreased when the niobium becomes superconducting. Now, this is even more evident if we use a thicker layer of niobium, for example, very evident for 60 nanometers of niobium. And it seems to suggest that as the niobium becomes superconducting, obviously less spin can propagate through it. Now, this picture is quite in agreement with our understanding of superconductors. Our intuitive picture that spin can only be transferred by quasi-particles. Now, you know that in a superconductor, below the transition temperature, there is the opening of a gap in the density of states. Now, the particles that live below the gap are Cooper pairs, and they are in a singlet state. So they are intrinsically unsuitable to transfer spin in a superconductor. However, particles that live above the band gap are single particles called quasi-particles that can be spin polarized and can transfer spin as in a normal metal. Now, the problem is that the spin generated by spin pumping have a typical energy scale of phi hf, where h is the Planck's constant, f is the frequency, the resonance frequency, and phi is the precessional angle. And while above the superconducting temperature, these energies are accessible above the band gap, when the niobium turns superconducting, these states are no longer accessible, and therefore quasi-particles cannot as easily diffuse into the niobium, and spin transferred through the niobium is suppressed. Now, in this graph here, you see the dependence of the resonance line width as a function of temperature for different thicknesses of niobium. In agreement with this picture, we see that at the transition temperature, which is represented by the dotted lines of the corresponding color, the damping, the line width, is immediately suppressed. Now, to further convalidate this picture that spin is transferred into the niobium via quasi-particles, we use the existing theories of spin pumping based on diffusive transfer of spin, just developed for normal metals, to completely map our results. So this graph here represents the niobium thickness dependence of the Gilbert damping. The continuous line is a fitting obtained with existing theories of spin pumping for normal metals in a diffusive regime. Now, the diffusive regime is justified also in our case because the mean free path of charges in niobium is about 6 nanometers, which is below any thickness that we have used. Now, the way in which we take account, well, differently from a normal metal, here we just need to take account of the opening of the superconducting gap below the transition temperature, which basically reflects in a lower population of quasi-particles above the band gap. Just here you see that we took account also of the inverse spin, of the inverse proximity effect. Indeed, the gap in the niobium only linearly opens up, and it's only fully open at a length of 13 nanometers, which corresponds to the Cooper pair coherence length. But anyway, here on the bottom graph, you see that the effective spin diffusion length into the niobium is plotted as a function of temperature for 60 nanometers niobium, and it basically at the transition temperature decreases to about 20 nanometers. Now, if we try to associate a time, a spin lifetime to this length, we find that the spin lifetime is determined by the lifetime of quasi-particles before they decay into Cooper pairs. Now, in a superconductor, the way in which quasi-particles decay into Cooper pairs is under reflection, for which a quasi-particle of a certain spin couples up with another quasi-particle of opposite spin to form a Cooper pair. But in this way, obviously, the spin information carried by the quasi-particle is lost in the Cooper pair, which is in a singlet state. So the fact that the lifetime of spin into the niobium corresponds to the lifetime of quasi-particles further confirms our model that spin propagates in the niobium via quasi-particles. Now, this is so the fact that we understand spin transfer through the superconductor is a good news. The fact that we can apply standard models on spin pumping to the niobium is a good news. The bad news is that there is obviously a resistivity associated to quasi-particle transport, so we're not talking about dissipationless spin transfer. However, there is something interesting happening in the second layout structure that gives us hope on the dissipationless spin transfer of, into the niobium. Now you see here, I'm plotting the temperature dependence of the ferromagnetic resonance line width in this second layout structure, in which platinum is grown in contact with the niobium on the opposite interface with respect to the permalloy. Now you see that for the thickest niobium layers, also in this case, the ferromagnetic resonance line width is drastically reduced at the transition temperature. But you see something strange happening at intermediate thicknesses, where the ferromagnetic resonance line width increases when the niobium turns superconducting. So this seems to suggest that somehow spin transfer through the niobium is encouraged, is increased when the niobium turns superconducting. Now this is also seen in this graph here, where we plot again the ferromagnetic resonance line width as a function of niobium thickness. Now, above the superconducting temperature, we can fit again very well our results with the existing theory of spin pumping elaborated for normal metals. Below the superconducting temperature, which corresponds to these lines here, there is no way we can fit our results. Now you see that also one thing is that for thickest niobium layers, the trend of decreasing line width with decreasing temperature, as we were observing in the first layout, is maintained. But this trend is completely inverted at lower thicknesses of niobium. So the interesting thing is that the highest line width that we measure here is even higher than the line width in the limit of very thin niobium layer as at room temperature, where basically all spin is pumped, is dumped in the platinum. So from this data, it seems like the niobium in the superconducting state is even a better spin sink than platinum, which is completely against our intuition of spin transfer mediated by quasi-particles. So we need to abandon the idea that in this case spin is transferred via quasi-particles, and we must accept the idea that it can be transferred by Cooper pairs into the superconductor. Now, in the past literature, there have been two different mechanisms by which spin can be transferred in the superconductor via Cooper pairs in a singlet state, as they are in a BCS superconductor. And these two mechanisms are cross-Andreev reflection and electron co-tunneling. Now, so we've seen that in an Andreev reflection, a single particle from one interface of the superconductor pairs up with an opposite spin to form a Cooper pair. Cross-Andreev refraction is basically the same thing, but the single spin on one interface pairs up with opposite spin on the opposite interface to form a Cooper pair. And this gives rise to a net spin current within the superconductor, which is carried by Cooper pairs in a singlet state. Now, in this electron co-tunneling, we have that two electrons of opposite spin co-tunnel simultaneously from two opposite surfaces, forming a Cooper pair in the niobium. And also this mechanism gives rise to a spin current, which can therefore transfer angular momentum from one interface to the other. Now, obviously, for these two mechanisms to be relevant, you understand immediately that the two interfaces must talk to each other, because two events from two opposite interfaces must happen coherently. And in our case, the maximum increase in line width that we observe occurs at 30 nanometers, which is almost twice as much as the Cooper pair coherence length. So for our 30 nanometers niobium film, the interface with the permalloy doesn't talk at all with the interface with the platinum layer. So it seems like these two mechanisms don't play any role. Now, to further investigate this hypothesis, we have played around with a superconducting gap into the niobium, trying to engineer it by taking advantage of the proximity effect. So basically what we have done, instead of growing platinum here, we have grown a bunch of different materials. For example, tantalum. Tantalum, due to the proximity effect, when tantalum is grown in contact with niobium, there is a superconducting gap opening in tantalum. So tantalum itself turns superconducting. So in this case, since cross-center of refraction and electron co-tunneling are both initiated by single particles from opposite interfaces, we would expect tantalum really not to contribute a lot to these effects, because tantalum is not a very good reservoir of single particles, as there is a superconducting gap opening in it. On the other hand, iron manganese, due to the antiferromagnetic iron manganese, has the opposite effect, and basically the exchange field closes the superconducting gap of niobium. So it should be, in theory, a better single particle, better quasi-particle reservoir to trigger the cross-center of refraction and electron co-tunneling. But this is not what we observe. So what we observe is that tantalum actually has the same, an effect very similar to platinum, in which the Gilbert damping increases below the transition superconducting temperature, almost as much as in platinum, whereas in iron manganese, the effect is opposite, and actually there is a decrease in the Gilbert damping below the transition temperature. So this again convalidates our idea that these two effects, cross-center of refraction and electron co-tunneling, cannot contribute to explain our result. Now there is a third possibility by which spin can be transferred through the superconductor, and this is the following. So spin can be transferred via Cooper pairs again, but these Cooper pairs are in a triplet state. Now, this to whoever is not an expert of superconductivity, like me, this seems quite strange, because we know that superconductors, Cooper pairs are in a singlet state. However, there has been a lot of work, both in theory and experiment, that studied the generation of Cooper pairs in the triplet state. So, in short, what happens is that when you have a homogeneous ferromagnet in contact with a superconductor, Cooper pairs that are both in a singlet state and in a triplet state, but with a zero spin projection over on the magnetization of the ferromagnet, are created. Now, both of these components are ripped apart by the strong exchange field in the ferromagnet, and therefore can diffuse to a very short length scale that is given by the ratio of the diffusion constant times the exchange field, which is a couple of nanometers usually. However, if you can imagine that if we had a way to rotate the component, the triplet component, Cooper pair component, into a state that had a non-zero projection on the magnetization of the ferromagnet, this component would propagate to much higher length scales. And this is because the exchange field would no longer rip apart this Cooper pair. Now, the way in which these Cooper pairs in a triplet state with zero spin projection to Cooper pair to a non-zero spin projection has been achieved experimentally has been to create a region between the homogeneous ferromagnet and the superconductor, a region in which of non-homogeneous exchange field. Now, this can be created by, for example, by engineering the presence of a block domain wall here, or it has been done by putting a spacer of holmium, for example, which is naturally in a spin helical phase. And in these devices, it has actually been shown that Cooper pairs can propagate to much longer distances in the ferromagnet, and this has been explained by this rotation of the triplet component. Now, in our system, we obviously have a homogeneous ferromagnet. We have a permalloy. The presence of platinum on the other side, which has been shown to play a quite crucial role, does not affect the magnetization of our permalloy in any way. So we are dealing with a completely homogeneous ferromagnet. However, we have something else. At the interface with between platinum and niobium, we have the Rashba spin-orbit field. And the idea is that these triplet Cooper pairs, instead of being rotated in this non-homogeneous exchange field, can be rotated in the spin-orbit field at the interface with platinum. Now, obviously, the first thing that seems strange is the fact that while triplet pairs with a zero spin projection are created at the interface with the ferromagnet, they should not talk, they should not feel the action of the spin-orbit field at the opposite interface. And this is because the thick thickness of the niobium is larger than the coherence length. So they shouldn't feel the effect of this field and they shouldn't be rotated by it. However, now I have to say that this is a work in progress. We are convalidating our theories by additional experiments and collaborating with some theorists. But what seems from some preliminary calculations is that what seems to play a very crucial role is the fact that the platinum is very close to a ferromagnetic transition. So this means that it has a very high spin susceptibility. And this, combined with a Rashba, with a break of symmetry at the interface, is sufficient to open spin channels in long-range spin channels in the niobium, through which spin pumped from the permalloy can propagate. Now, at the same time, as spin arrives into the platinum, it increases the spin splitting in platinum and acts as a positive feedback that makes this effect even larger. Okay, so I think so. I don't want to add anything. Obviously, if you have questions, I'm happy to answer. Just leave you with a summary, and of course, I want to thank the funding bodies. Yeah.